This video is an introduction to probability distributions, specifically discrete probability distributions. So have a look at the spinner here on the right side of the page, the spinner right here. If I asked you how much money would you expect to win by spinning this spinner, think about how much you might expect to win and why you might expect to win that. Now, when I ask about expectations, expectations require us to look at the outcomes and their probabilities. And in fact, in the world of probabilities, we call this expected value. So the expected value is the predicted average of all possible outcomes. So for this spinner, you might think that the predicted average is just going to be the sum of all of the values that we can win. So $1 plus $2 plus $5 plus $20 divided by 4, because there are 4 values here. That would give us 28 over 4, which is equal to 7. But in this case, not all of the outcomes are equally likely. It looks like you were going to have a larger chance of winning $1 than you are of winning $20. So in this case, because all of the outcomes aren't equally likely, this probably isn't going to be the way to find the predicted average. So can you think of a way that you might be able to come up with an expected value for this game? What information might be helpful here to know about this spinner game? Well, I can give you some information. I can tell you that the angles in the picture are 145 degrees, 110 degrees, 70 degrees, and 35 degrees. So see if you can use those pieces of information to come up with a possible expected value. We'll revisit this problem at the end of the video today. So let's move on here. We're going to go through a couple of definitions just to make sure everybody's on the same page here. When we talk about a discrete function, for a discrete function, only certain number of inputs are allowed, or only certain values for inputs are allowed. So for example, if you consider shoe size is what we would call a discrete value. And the reason for that is that we can have a size 5 shoe, we can have a size 5.5, we can have a size 6, but we can't have a size 5.1234. That size doesn't exist. There are only certain values that our function can take on. On the other hand, a continuous function would have an infinite number of inputs allowed, and there wouldn't be any gaps between any input values. So for example, the mass of a newborn baby could be 4 kilograms, it could be 4.98 kilograms, and it could be any value in between those two values as well. So we call that a continuous function because there's no break between the different values. So the reason why we needed to differentiate between discrete and continuous functions is that, as I mentioned earlier, today we're going to focus on discrete probability distributions. So a discrete probability distribution is a function that provides, so we're looking over here, discrete probability distribution is a function that provides the probabilities of all possible outcomes. And we'll do an example in a moment where you can see what this looks like. And the last little bit of information that we need is a random variable. So a random variable is really just the set of all possible outcomes. We always denote random variables with capital letters, and often we use a capital letter X. Again, we'll look at all of this in an example shortly. So here's the example. We'll keep it fairly simple for the first one. So in this example here, we are trying to find the probability distribution of rolling a 6-sided die. So in this case, we're going to let X, our random variable, let X be the random variable that represents the results of rolling a 6-sided die. So we just want to know what are the possible outcomes of rolling a 6-sided die. So often it's helpful to display this in a table. So let me just copy a table over for us, and then we can use that table to show the distribution. Okay, so here's our table. And we've got our random variable. Now maybe before we get to the table, I'm just going to slide the table out of the way for a second. We'll just have a quick peek at a few things just to make sure everybody's okay here on the same page. So we've defined our random variable as rolling a six-sided die. So here's our random variable x. X is all, let's try that again. X are all of the possibilities from our little experiment here. And our experiment here is rolling a six-sided die. So the set of all possible outcomes when we roll a six-sided die is a 1, a 2, a 3, 4, 5, and a 6. So again, the random variable is this whole set. This whole set is x, our random variable. Now we use a lowercase x to represent the elements in that set. So in this set, we could say that x equals 1. We could also say that x equals 2, and so on. So this notation here, down here, is the probability that x is equal to, so the value in our set is equal to a certain value. So the notation's a little bit confusing and takes a little bit to get used to, but over time it should become a little bit easier. So I just want to emphasize here that the lowercase values are elements in the set. So these lowercase x's are elements in the set, and this here, capital X, is the set of all outcomes. And that's our random variable. So if we look at this distribution, these values in the table, these are all of the elements in our set from our random variable. They come from here. So when we roll a six-sided die, all of the possible outcomes are the numbers from 1 to 6. And this here just means what's the probability that x, the random variable, is equal to each value. So for this first entry in the table, in this column, we're really finding what's the probability that our random variable is equal to 1. In other words, what's the probability that we roll a 1? And the probability here is just 1 out of 6. There's 6 possible outcomes. And this is what we call a uniform distribution. Every outcome is equally likely. So we have a 1 out of 6, our probability is 1 out of 6 for each of these outcomes. So this is a little bit different from the spinner, where each outcome wasn't as likely. Because these outcomes are as likely, what we could do technically is just add up all of the values that we had, the 1 to 6, add these all up, and divide by 6. That only works for a uniform distribution, though, so we'll have to be a little bit careful there. Okay, so this is our probability distribution. It shows all of the possible outcomes and the probability for each of these. We could make a graph as well. I don't know if I'm going to be able to fit a graph in here. Let's see if I can just fit a small one in, maybe. When we graph this, I'll show you what the graph looks like, and then we can talk about how we go about graphing it. Really what we're doing is we're just graphing the outcomes and their probabilities. So here's what the graph would look like. Let me just copy this graph over, and then we'll have a quick peek. So here's what the graph would look like. Notice that the outcomes are along the bottom. So we have our values from 1 to 6 listed along the bottom. Possible outcomes. Here we are, 1, 2, 3, 4, 5, and 6. And the probabilities here. If we do 1 divided by 6, because that's the probability of getting each of these, 1 divided by 6 gives us 0.17 approximately, and that's the value, sorry, right up here, I kind of missed there. So this value here would be 0.17. So we can show this distribution in the table, we can show it in a graph, and I'm going to just move this out of the way for now so that we can come back to this table. And let me just clean up this little bit right here. All right, so we talked about the expected value because this is a uniform distribution, we should be able to just add the numbers from 1 to 6, divide by 6, and if we do that, let's go ahead and do that. So the expected value, and we use this capital letter E for expected value. So rather than writing expected value all of the time, this is the expected value of our, so expected, see if I can squeeze that in here. So the expected value in this case would be 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then we would divide that all by 6. And when we add all of those up, we get a total of 21 divided by 6, which equals 3.5. Now I know it seems a little bit weird to have our expected value to be a value that we can't actually get. But if we were to do this experiment 10,000 times and take an average of all of those 10,000 times, we would see that on average we got a number that was 3.5. That's what the expected value means. I want to show you a slightly different way to calculate expected value. As I mentioned, this only works for a uniform distribution. So let's look at the expected value for a, well, that will work for all types of distribution. And in order to do this, what we're going to do is we're going to add a column into our table here. So this column here is going to take our x value, our random variable, and multiply it by the probability that that random variable happens. So if you remember with the spinner, we said that the probabilities weren't all the same, so we needed to account for that, and this is how we do that. So here's our x value over here, and we're going to take that x value and multiply it by the probability of x. So we'll just do that in this last column. So 1 times 1 over 6 is just going to be 1 over 6. Try to fit this in here. 2 times 1 over 6 will be 2 over 6. 3 times 1 over 6 will be 3 over 6. I'm just leaving these in unreduced form because what's going to happen here in the end is we're going to add these all together. So we're going to want to have a common denominator. So we'll get 4 over 6, 5 over 6, and 6 over 6. And it turns out that if we add this column up, so we take this column, add it all up, we get the same thing that we had over here. We have 1 plus 2 plus 3 plus 4 plus 5 plus 6. So that was 21/6, which was equal to 3.5. We get the same result. So you can see that you get the exact same result. The nice thing about doing it this way is that this method will work for any type of distribution. It doesn't have to be uniform. So the spinner example that we did earlier, this will work for it. All right. That takes us to the formula for expected value. As I mentioned earlier, this notation here means expected value. So E at x is just expected value. The formula looks complicated, but we'll walk through it. Hopefully it'll make a little sense. Don't forget this sigma notation. Sorry, there was an n at the top here that I've cut off. Let me just add that back in. There was a little n right here. So the sigma notation just means the sum of. So this means the sum of all of the x times the px's. The I down here basically is an index number. It starts at 1. So this says, hey, let's take x1 and multiply it by the probability of x1 happening, which is exactly what we did in the table up here. We took our first x value right here, multiplied it by the probability, and that's what went in this entry here. And then we go to the second one. I then becomes 2. So I starts at 1. Second time through, I is 2. So then we take x2 and multiply it by the probability of x2 and so on. And so here's the long way to write that out. If the summation, the sigma notation is throwing you off a little bit, all the expected value means is take all of the values in your random variable, all of the x values, multiply them by the probability, and then add all of those together, and that will give you the expected value. So we've looked at a uniform distribution. we should look at a non-uniform distribution to show what that looks like. So here's an example of a very simplified Plinko game. Hopefully you know the idea behind Plinko. The idea is that you would take a ball or a chip or something, and you would drop it in here at the top, somewhere at the top, drop it down, and you would try to get as much money as you can. So this one is a little bit simplified because it's there are some sort of low values here. Yeah, this is a game of The Price is Right, I guess. So many of you have probably seen it. If not, check it out. Do a quick search for Plinko videos, and you'll see kind of how the game works. So the way that our simplified version is going to work is we are going to make, as I said, a very simplified version of this game. We are going to say that we must drop our little chip that is in the top at the very center of the board, and that's just going to simplify things for us a little bit. Otherwise, this problem gets really big. So let's keep it fairly simple, and I'm just going to have a look here and look at simplifying this for us. If we start in the middle, we're going to count basically how many possible ways we can get to each one of the locations on the board. And this starts to actually look a whole lot like Pascal's triangle. So there was kind of one way to get here. You know, we drop our Plinko chip in here. We can get here one way. We can get here one way. And we can kind of keep going down the sides one way. Or we can get to the center here from here or from here, so there are two ways here. And if we do this all the way down, we get something that looks a whole lot like Pascal's triangle. I'm going to just save us a little bit of time and copy that in here for us so that we can see what that looks like. Just give me a second. All right, so it ends up looking, sorry about that. Let's try that again. It ends up looking like this. I'll make it a little bit bigger. In fact, we can just stick it right on top of the Plinko board that we have, or maybe beside. Make it a bit bigger. Yeah, we'll stick it right on top. Hopefully you can see those numbers. There's the Pascal's triangle that I was talking about earlier. So you can see Pascal's triangle very nicely here. And so what we're trying to do is to figure out the expected value here. We want to figure out how much money can somebody who plays this game expect to win over time. So here are all of the sort of number of ways. Let me just highlight those. The number of ways to get to the bottom of the board are all listed here. So we can get to this spot 44 times, 208 times, and so on. It turns out that these are all of the ways that we can get to the bottom of the board. If we add all of these up, we get 4,000. You can do that if you want, just to double check. But the sum of all of the numbers down here is actually equal to 4,000. So we're going to start by saying, let's let our variable, let x equal our random variable. So let x be the money we can win. Let x represent the money we can win, or the winnings. We'll call them winnings for this game. So if you look at the board, the winnings are down here at the bottom. We can win $0, $2, $1, or $4. And I think that's it, right? We've got 0, 1, 2, and 4. So again, we're going to make a table that displays those outcomes for us so that we can find the expected value. So again, I'll just copy a table over. So here's the table, and we're going to list our random variable is our winnings. So our possible winnings are, we can either win $0, we can win $1. I assume these are dollars. We can win $2, or we can win $4. So now we need to figure out, well, what's the probability of winning each of these amounts of money? So in order to find the probability of winning each of these amounts, what we have to do is look at, well, let's start with 0. Here's 0 right down here. We can get to 0 792 ways here and 792 ways here. So the probability for 0 I don't have enough room to write this in the box, but I'll put it down here. So the probability that x, our random variable, is equal to 0 is equal to the 792 ways to get to the one 0 plus the 792 ways to get to the other 0. And all of that is over the total number of possible outcomes, which is 4,000. So this is, what's that, 1,584 out of 4,000. And I'm just going to turn that into a decimal so that we can use it. That's 0.396. So this value here is 0.396. And we would do the same thing for $1. Well, the $1 happens here. So 494, and it happens over here as well, 494. So the $1 winnings then is 988. I think I can squeeze that in here. 988 over 4,000. And if we plug that into the calculator, we get 0.247. So almost a 25% chance of getting $1. Do the same thing for $2. So for the $2, there's a few ways that we can get $2. I guess 2 happens right here. So 208. It happens here at 924, and it happens here for 208. So we're just going to add those all together. And if we add all of those together, I think we get 1,340. And again, that's still out of 4,000. And that is equivalent to a decimal 33. Sorry, that's a bad looking 3. 335. And then the last one is how many ways can we get a 4? Well, the 4 happens here, and it happens over here as well. So there are 88 out of 4,000 ways to get $4, which is equal to 0.022. So we've now calculated the probability of each of these events happening, winning 0, 1, 2, and $4. We want to calculate the expected value. In order to do that, we're going to need this column over here where we take our x values, each of our random variable values, and we multiply it by the probability of that happening. So 0 times 0.396, that's not too hard to figure out. That's just equal to 0. And then we're going to do 1 times 0.247, which will be 0.247. Should I put in, why don't I add in sort of the calculation here so you can see what happened. Let's try that again. So this was the x times the probability of x. And so we did 0, that's our x value, times the probability of x. And that gives us 0. And then we do 1 times 0.247. And that gives us 0.247. 2 times 0.335. And that gives us 0.67. And then lastly, 4 times 0.022 gives us 0.088. Just notice my 7 up here doesn't look too good. Okay, so we've now done our random variables times the probability. And remember, to find the expected value here, the expected value is just the sum of all of these values. So we add up all of these. So this is the sum of all of the x times the px's. And if we add those all up, we get 1.005. What this means is that in the long run, we can expect to win just over $1. Now, casinos and any kind of gaming place that you go to, they use these values all the time. So if this is a game that's offered at a casino, they know that your expected winnings are $1, just over $1. The goal of the casino is to make a profit. If they charge you $1 for this game and you're going to win on average just over $1, the casino is going to go out of business. I know that half a cent doesn't seem like very much, but half a cent multiplied by millions of games, millions of people, and so on starts to add up. So the casino wants to make the game interesting to you. So they want to make it so that you're going to seem like you're winning, but in the long run, you're going to actually end up losing by a little bit. So in this case, you wouldn't charge $1 for this game if you were running this game as an event, as a fundraiser, because you would lose money in the long run. You'd need to charge more than $1. You don't want to charge $5 because then in the long run, the player ends up losing $4 and they start to not be as excited. But maybe somewhere around $1.50. Maybe $1.10. It sort of depends. So that's what expected value is. That's how we use it. This was a non-uniform distribution. I didn't show you the graph, but maybe I should show you the graph of what it looks like. Same sort of graph as a uniform distribution look like. Let's see if I can paste it in here and not lose too much information. All right. So in this graph, we have the probabilities listed along the bottom. So, sorry, not the probabilities. We have the outcomes listed along the bottom. So you can win $0, $1, $2, or $4. And we have the probabilities listed along the side. This graph was just made using a spreadsheet. That's a nice quick way to do it. Again, because these are discrete values, we should maybe talk about the difference between a bar graph and a histogram. Histogram. What we want to do here is that we need to leave spaces. These values are not continuous. There is no value between 0 and 1, so that's why we leave a space here between the bars that we create. So this is actually a bar graph, and as I said earlier, we're looking now just at discrete probability distributions. So all of your graphs should be bar graphs with spaces in between the bars because they're not continuous. All right, that takes us to our last slide here. I asked at the beginning of this video what the expected winnings are from the spinner. Why don't you take some time now, fill out the table, and see if you can calculate the expected value. Just a reminder, something that might be useful to you are the angles here. I wrote them down on the first slide, but let's see if we can jot them down here so that you can have them. So the largest angle here is 145 degrees. I think it's easy to pick out which angle is which. The next angle is 110 degrees. Then we have a 70-degree angle, and finally a 35-degree angle. So the angle will be useful to figure out what percentage of the circle and help you find the probabilities.